Welcome back to our series on alkyne reactions. In this video, we turn our attention to hydration, adding water across a C-C triple bond. Unlike alkenes, which undergo acid-catalyzed hydration with relative ease, alkynes are far less reactive towards simple electrophilic addition and therefore require a stronger catalyst. Here, we'll examine the hydration of the terminal alkyne, propyne, using aqueous sulfuric acid in the presence of mercury 2 sulfate. Starting with propyne, water adds across the triple bond following Markovnikov's rule. The hydroxyl group attaches to the more substituted carbon, while the hydrogen atom adds to the less substituted terminal carbon. The initial product formed is an enol, essentially a vinyl alcohol, meaning it contains both an alkene and an alcohol functional group. However, enols are highly unstable. They rapidly rearrange through a process called tautomerization to form a more stable isomer. For a terminal alkyne like propyne, this rearrangement yields a methyl ketone. Therefore, the final product is acetone. The mechanism involves mercury-catalyzed addition followed by acid-catalyzed tautomerization. We will break this down chronologically. Step 1. Mercurinium-like Intermediate formation. The reaction begins with the electrophilic activation of the alkyne. The pi electrons of the triple bond attack the mercury 2 ion, derived from HgSO₄. This forms a mercurinium-like intermediate. This step is crucial because Hg2+ is a strong enough Lewis acid to polarize the alkyne pi bond, making it susceptible to nucleophilic attack, something simple protonation cannot efficiently achieve for alkynes. Step 2. Nucleophilic attack by water. Water, acting as the nucleophile, attacks the mercurinium-like intermediate at the more substituted carbon C2. This regioselectivity arises because C2 bears a greater share of the partial positive character in the transition state, stabilized by the neighboring methyl group. Ring opening then produces a vinyl organomercury intermediate, in which water becomes bonded to C2 while mercury remains attached to C1. Step 3. Deprotonation. A base in the solution, often another water molecule, removes a proton from the positively charged oxygen atom. This neutralizes the intermediate, giving an organomercurial enol. At this point, the hydroxyl group is on the more substituted carbon, and the mercury atom is on the terminal carbon. Step 4. Demercuration, replacement of mercury with hydrogen. Protonation occurs at the terminal carbon C1 of the organomercurial enol. This protonation happens concurrently with heterolytic cleavage of the CHG bond, releasing Hg2+ and regenerating the catalyst. The resulting electron deficiency is immediately stabilized by resonance donation from the oxygen atom, yielding the neutral free enol, Prop1e2-ol. Step 5. Acid-Catalyzed Keto-Enol Tautomerization. With the free enol now formed, the molecule quickly rearranges to its more stable keto form under acidic conditions. This conversion proceeds through a protonation-deprotonation sequence. First, the pi electrons of the enols double bond attack a proton. Protonation occurs at the terminal carbon C1, placing the positive charge on the adjacent carbon C2 and generating a carbocat ion that is stabilized by resonance with the oxygen atom. Next, this intermediate reorganizes its electron density. The oxygen donates a lone pair to form a CO double bond, producing an oxonium ion in which the positive charge resides on the oxygen. Finally, water removes the proton from the oxonium oxygen. This deprotonation restores neutrality and completes the formation of the carbonyl group, giving the final product, acetone. Why does the equilibrium favor the keto form? The keto tautomer is favored at equilibrium because the carbonyl CO double bond is much stronger and more stable than the CC double bond and OH bonds in the enol. This greater bond strength lowers the overall energy of the molecule, making the ketone form thermodynamically preferred. Now, let's briefly look at internal alkynes. These alkynes are generally less reactive toward hydration than terminal ones. In fact, under strongly acidic conditions, some internal alkynes can hydrate even without mercury, although Hg2+ still speeds up the reaction significantly. Because water can add to either carbon of the triple bond, mixtures of ketones are commonly formed from unsymmetrical internal alkynes. In contrast, symmetrical internal alkynes produce just one ketone, since both sides of the triple bond are equivalent. Mechanistically, the process follows the same general pathway we saw earlier, but without the regioselectivity concerns that appear in terminal alkynes. Let's summarize. Step 1. The alkyne donates electron density to Hg2+, forming a Mercurinium-like intermediate. Step 2. Water attacks the more substituted carbon, breaking the Hg-mediated interaction and generating a vinyl organomercury intermediate. Step 3. A base removes a proton from the oxonium species, producing the neutral organomercurial enol. Step 4. Protonation at the terminal carbon and concurrent cleavage of the C-Hg bond release, Hg2+, and generate the free enol. Step 5. The enol undergoes acid-Catalyzed tautomerization to form the more stable ketone. Let's organize by keywords. Markovnikov's rule ensures that OH adds to the more substituted carbon, giving a ketone rather than an aldehyde. Keto-Enol Tautomerization is the rapid conversion of an unstable vinyl alcohol into a more stable carbonyl compound. Methyl ketone is the characteristic product formed when a terminal alkyne undergoes oxymercuration. Mercury catalysis refers to the role of Hg2+ in activating the alkyne toward nucleophilic attack and directing the reaction along the Markovnikov pathway. To wrap up, those who wish to deepen their understanding of alkyne hydration are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.